Okay, let's go back to our example function. When we take the message signal and we mix it with the carrier signal, this is the signal we get for the double sideband suppressed carrier amplitude modulated signal. For demodulation, this signal is in turn multiplied with a replica of the carrier signal, and the result of that multiplication is shown here. And you can see in the peaks of the signal, the signal R of t, in the peaks of the signal R of t, you can see the outline of the original message signal. When we take the fast Fourier transform of the signal R of t, we get the spectrum that is shown here. You can clearly see the spectrum of the message signal shifted back down to baseband, and you can also see copies of the message signal spectrum shifted to twice the carrier frequency. If we use a low-pass filter, we can easily isolate that portion of the spectrum that has been shifted down to baseband, and you will note that that is a replica of the spectrum of the original message signal. I then took the signal R of t. This is the signal that comes out of the mixer in the synchronous demodulation system. I took this signal R of t and I used a digital low-pass filter to retrieve the original signal as shown in this diagram. The light blue line is the original message signal. The dark line is the signal that comes out of the low-pass filter. And you'll note it has a bit of a transient response at the first, but as you move beyond that, it is a very good replica of the original message signal with only a small time delay. We need to investigate one last matter. Recall that with synchronous detection, we had to mix the modulated signal with an exact replica of the carrier signal. What happens if the replica is not exact? So let's consider again the signal R of t that's coming out of the mixer. And I can write that equation down. R of t is equal to x of t times AC cosine 2 pi fc t. And now we will mix that with a close replica of the carrier signal, amplitude AD cosine 2 pi. Instead of the carrier frequency, though, I'm going to make it the carrier frequency plus a bit of error, and that error in the frequency I will call delta F. And just to be complete, then that multiplies T, and let's then also put a phase error, phi, into that signal as well. So we have both frequency error, delta F, and we have phase error, phi. And we want to see how this will affect our ability to demodulate the signal and retrieve a copy of the message signal. So let's see, we would have now R of t equal to AC times AD, those are both constants, times x of t. And now we have cosine A times cosine B. And the proper trig identity is going to be 1/2 cosine of the difference of the angles. So when we take the difference of the angles, I'll take 2 pi fc plus delta f times t plus phi and subtract 2 pi fct. That will give us a 2 pi delta f times t plus phi. That's the difference of the angles plus a 1/2 times the cosine of the sum of the angles. And the sum of the angles is going to be 2 pi. And now we'll have 2 times fc plus delta f times t plus phi. Okay. Okay, so this is the difference of the angles. And this second one is the sum of the angles. Now this signal is then passed through a low-pass filter, and we will get y of t equal to the low-pass filter version of r of t. And I don't want to write it all out, so I'll cut to the chase. The low-pass filter will block this high-frequency component, and let's presume that it will pass the low-frequency component. What we get is a 1/2 ACAD times x of t times cosine of 2 pi delta f t plus phi. Okay, this is the output of the low-pass filter. Now, for us to retrieve some copy of x of t, that is going to require that delta f, the frequency error, be exactly 0. Otherwise, what we have is a slow, let's presume a slow-moving cosine that is that's changing the amplitude of our message signal. It's going to we won't be able to retrieve the message signal. So delta f must be 0. Let me write it out. 0 to demodulate the signal. So that is our first conclusion. Now, if delta f is equal to 0, we would have y of t equal to 1/2 AC times AD times x of t times cosine of phi. Now, phi does not have to be 0. If phi is 0, cosine of 0 is 1, and that works out perfectly well. But we'll be able to get a copy of the original message signal as long as phi is not close to 90 degrees, or plus or minus 90 degrees. If the phase difference, the phase error is close to 90 degrees, then the cosine of 90 degrees is going to be nearly 0, and that's going to take out the message signal. So phi must not be close to 90 degrees. It can be any other angle, because if it's an angle that is not close to 90 degrees, cosine phi is simply another constant that we can accommodate by increasing the gain of an amplifier. Okay. Well, I've got your attention. Would anybody know how to solve this thing? It's a it's kind of a Rubik's Cube in the shape of a ball. Have not had any luck solving this so far. Oh well. Another day.